from Oxford, who actually had the first inspiration of this institute and carried through and pushed everybody to actually making it a reality, and I believe a great success. So thanks very much. John will talk about satisfaction of the eigenvalue constraint on the Q tensor.
Thank you very much, Claudio. It's a great pleasure to be able to speak at this workshop, and thanks to the organisers for inviting me. So this is joint work with Apala Majumdar, who's at the University of Bath, and there are actually one or two little developments that have been included, which I worked on while I was here, so there's a little bit of productivity. Okay, so let me remind you first of all what the Q tensor is. Is there a pointer? There isn't a laser pointer.
That long stick in the corner.
Oh, longer stick. Okay, right. So let me remind you what the Q tensor is. So let's consider a pneumatic liquid crystal consisting of rod-like molecules whose individual orientations can be described by a pair of antipodal unit vectors, P, or another way of describing it is by the matrix, the tensor product of P with itself, because that's something that is invariant to changing P to minus P. Thank you very much. Thank you very much. Central one. Yeah. So the invariance of P to minus P is that we want the theory to be invariant to the head-to-tail symmetry of the molecule. And so the description of molecular orientations in some sufficiently small space-time neighborhood of a fixed point xt can be described by, or the hypothesis is that it can be described by a probability measure mu, which depends on x and t, but I'll drop the dependence on x and t for most of the talk. On the unit sphere, a probability measure on the unit sphere, S2, which satisfies the symmetry relation due to head-to-tail symmetry of the molecules, mu of a set E is mu of minus E for any subset E of S2. And then the de Gennes Q tensor is a normalized second moment of this probability distribution. It's given by integrating over S2 the tensor product of P with itself minus a third the identity. So it measures the deviation of the second moment of mu from its isotropic value. The first moment of mu is 0 due to the symmetry condition, and so that it's in the second moment that you get the first non-trivial information. So if you look at the definition, you see immediately that Q is a symmetric matrix because you're integrating a symmetric matrix. Its trace is 0. That's why well, you can take the trace through the integral, and the trace of P, tensor P is just 1. The trace of a third, the identity is 1. That's why this 1/3 of the identity has been subtracted off to make it the trace 0. And now, if you look at Q plus 1/3 the identity matrix, that's a symmetric matrix, and it's a non-negative matrix, because if you hit this with a unit vector E, so QE dot E will give you the integral of P dot E squared minus a third. Okay, so that means that the Q, which is a symmetric matrix, it has 3 real eigenvalues. The minimum eigenvalue of Q has to be bigger than or equal to minus a third if you accept this definition or derivation of the Q tensor. Now, what happens if the minimum eigenvalue is equal to minus a third? Then when you form QE dot E, you get that the integral of P dot E squared against the measure is 0. So that means that mu, the measure, is supported on the great circle perpendicular to E. For example, it could be half a Dirac mass at E hat plus a Dirac mass at minus E hat, where E hat is perpendicular to E. And that would correspond to perfect alignment of the molecules parallel to the direction E. Now, if you regard such perfect alignment as not being physically reasonable, then you would expect that not only is lambda min bigger than or equal to minus a third, it's strictly bigger than minus a third. And that implies, because the trace of Q is 0, so the sum of the eigenvalues is 0, that in fact the maximum eigenvalue of Q would be strictly less than 2/3. And so the question I want to ask and try to answer in this talk is, how are these inequalities to be preserved in the theory? Because we'll have certain governing equations. Will they or will they not preserve these eigenvalue constraints? Now, for statics, we typically minimize the total free energy at temperature T, which is a function of Q at the temperature T, which you get by integrating over the region occupied by your liquid crystal, a free energy density that depends on Q and on the spatial gradient of Q and on temperature. We try to find a Q that minimizes this, or at least makes it stationary, subject to suitable boundary conditions. And usually we decompose this free energy density as the sum of bulk and elastic terms. So first of all, you put the gradient of Q equals 0, and then you get some function that just depends on Q and T, and then you have to subtract off from T this expression, and that's the bit that we call the elastic term, which really depends on the gradient of Q. So this is the bit that doesn't depend on the gradient of Q. This is the bit that does. So often the following forms are used, or forms like this. So for the bulk energy, a quartic form, so this is an isotropic function of Q. There are various coefficients, a B and a C and an A. The A is usually taken to depend on temperature, to be another constant alpha times T minus some critical temperature. So that's a quartic for the bulk energy. And then for the elastic energy, well, one has more choices. So I'm going to take, as a sort of representative choice, a linear combination of four invariants, four quadratic functions of Q and the gradient of Q, with coefficients Li, which could depend on the temperature. And the first three of these, I1, I2, and I3, are the only possible isotropic functions of the gradient of Q alone, which are quadratic. And the fourth one is one of 6 possible cubic terms. So I just choose this one as a representative one and put a coefficient in front of it. So now, for these forms of CB and of CE, energy minimizers Q, if they exist, do not in general satisfy the eigenvalue constraints. So for example, if you look at MBBA with experimentally measured coefficients, then the scalar order parameter of the nematic state exceeds 1, so that's a violation of the eigenvalue constraints for temperatures only 7 degrees below the nematic initiation temperature. Furthermore, there's a problem that I briefly mentioned in the first workshop, which is that if L4 is not 0, then for any boundary conditions, the energy that I wrote down, when I forgot the dependence on T there, is unbounded below. So it turns out that these two issues are related. So we propose that the eigenvalue constraints are satisfied because in a physically correct model, the bulk energy should satisfy the condition that it blows up as the minimum eigenvalue goes to minus a third, which it doesn't do in the quartic model, of course. So such a suggestion was made by Jerry Erickson in the context of his model of nematic liquid crystals. And we're going to show how an CB which satisfies that can be constructed on the basis of a microscopic model. And you can regard this piece of research as a sort of rigorous analysis and development of work of Catriel, Kwenzel, Luckhurst, and Slucking in 1986. So the microscopic model is the Onsager model, in which the probability measure mu is assumed to be continuous with density rho, depending on the unit vector p in S2. And the bulk free energy at temperature T has the form the usual form of the Helmholtz free energy, an internal energy minus temperature times the entropy. And in this theory, the entropy is given by minus the integral of rho log rho over the sphere S2. Maybe I should have had a Boltzmann constant in that, KB. And with the Meyer-Salpy molecular interaction, the internal energy is given by this double integral. So kappa is a coupling constant, and then you integrate with respect to p and q, a third minus p dot q squared, rho of p, rho of q. So that's a term which is minimized when p is parallel to q. So if you think of p and q as two different molecules, minimizing this term wants to make the molecules aligned, whereas the entropy term wants to jiggle them about, so there's some kind of competition between them. Now the 1/3 here just adds a constant to u, so it might as well not be there. It adds a constant because the integral of rho is 1. It's a probability measure, but it's put there to get a nice formula in a moment. Now, I'm going to assume in this talk that kappa is independent of t. So one of the things I've learned during this program is that that's not so clear that that's correct. But in fact, in this term, there can be entropic effects as well. However, I'm not going to go into that. So I'm going to assume that k is independent of t. If k depends on t, then the analysis would be similar. It would just change things like where phase transformations occurred and so on. All right, now, so let's look at the Q tensor corresponding to this particular continuous distribution of molecular orientations rho. So here it is, the integral of p tensor p minus a third the identity times rho. And let's compute the Euclidean norm squared of this matrix. So that's the trace of Q transposed. So that is, in fact, just the double integral. So I write it down twice with a p and a q, and then I take the dot product of everything. So that's the double integral of this integrand times the same integrand with p replaced by q. And you work it out, and you find that it comes to exactly the term that appears in the Meyer-Salpy internal energy. See, exactly, without the kappa and with the sign different. So that means that, in fact, u of rho depends on rho only through the Q tensor. Okay, so u of rho is minus kappa q of rho squared. And so the free energy is a of rho t is t times, again, I should have probably put this Boltzmann constant in there, integral of rho of p log of rho of p minus kappa q of rho squared. So now, the idea is that given a particular, we want to get a bulk energy that as a function of Q. So let's take a particular matrix Q and minimize this IT. I thought I eliminated all the thetas. So sometime when I did the talk, the temperature was theta, but now it's capital T. So there was one that I failed to eliminate last night in the early hours. So what you do is you minimize I of rho t subject to the constraint that the Q tensor corresponding to rho is your matrix Q. So that means that you want this to be capital T times the infimum of over rho with Q of rho is equal to Q of the integral of rho log rho minus k Q squared. And you see that since the rho doesn't appear explicitly here, so that's a great advantage of the Meyer-Salpy model. We only have to worry about minimizing this term, but subject, of course, to the constraint that the Q tensor is the right thing. So, this I also has another change of notation which I forgot to change. This I wrote previously as A of rho and T, not I of phi theta of rho. So this was the. Let me just go back and show you what that was. So A of rho and T. Okay, this is what I'm supposed to be minimizing. Excuse me. Okay, so now so in order to do this, we just need to understand how to minimize I of rho, which is the integral of rho log rho, subject to this constraint that q of rho is q. So now, let's try and set that up a little bit more precisely. So given a q, which is symmetric, trace-free, and satisfying that the minimum eigenvalue is strictly bigger than minus a third, I'm going to seek to minimize I of rho, which is the integral of rho log rho, on the set of admissible functions, L1 functions on the sphere, which are non-negative, and satisfy q of rho is equal to q. So a couple of remarks. If rho is in AQ, then you can take the trace of this relation and you recover integral of rho is 1. So I didn't put that explicitly into here because it's automatic. Secondly, I didn't put the symmetry condition in, which I also could have done. Rho of p is rho of minus p. That's because it turns out that the minimizer in this space automatically satisfies this condition. So you don't have to worry about it. Well, the first thing you might ask is AQ non-empty? So is there a rho that gives the required eigenvalue? So let's, without loss of generality, we can assume that Q is diagonal with eigenvalues lambda 1, lambda 2, and lambda 3. So this is a singular measure which satisfies that the corresponding Q is our given matrix Q. Right? Now, on the other hand, we don't want a singular measure. We want an L1 function rho. So what you do is you smear this out a little. So instead of having sort of direct masses on the sphere, you just make them little patches which approximate the support of the measure, and then it's not difficult to check that you can find an L1 function which satisfies this. Now, of course, you've got to be a little bit careful, because had one of these eigenvalues been equal to minus a third, that would not have been possible. Okay, so you do have to use the fact that lambda I is strictly bigger than minus a third. Of course, it's possible for a singular measure, but not for an L1 distributed measure. And from the fact that this is non-empty, it's not difficult to show that, in fact, I attains a minimum at a unique rho, which I'll call rho sub q. So I'll say a bit more about how this is done in a second. Now, what is the Euler-Lagrange equation for I, it should say? Okay, the Euler-Lagrange equation for I. So here's a theorem that, so here's q, diagonal lambda 1, lambda 2, lambda 3. Then rho sub q is given by this Maxwellian, it's a constrained Maxwellian, so exponential of sum of mu I pi squared divided by its integral over the sphere, which I'll call z, the partition function. And the mu I, which are unique up to adding the same constant to each, solve the equations that the gradient of the log of the partition function is equal to lambda I plus 1/3. Okay, so the minimizing rho sub q then is semi-explicit. It's given by this explicit formula, but on the other hand, you need to know what the mu i's are, and to get the mu i's, you've got to solve these algebraic equations, which do depend on this integral. Now, the way we did this to start with was to prove the existence by the direct method of the calculus of variation. So that's actually quite easy, because rho log rho is a superlinear function of rho. So that gives you some weak compactness in L1. It's not important if you don't understand these details. But you can do it that way. So you could directly prove the existence of a minimizer, and then you could try and show that it satisfies the Euler-Lagrange equations. Now, of course, these are constrained Euler-Lagrange equations, so that there are Lagrange multipliers that appear. So you can carry this through, but it's a bit irritating to do it because of the following snag, that you're minimizing the integral of rho log rho, and rho has to be bigger than or equal to 0. So it's not obvious a priori that rho couldn't be 0 somewhere, maybe even on a set of positive measure, or that perhaps it wasn't bounded away from 0. So that's an irritation when you try to calculate the Euler-Lagrange equation, because if you take rho plus t times some w or something, then rho plus tw might well be, so you want to integrate, you want to carry out d by dt of I of rho plus tw at t equals 0, but rho plus tw could be negative, so I of rho plus tw could be infinite. So that's irritating, but you can carry out this procedure if you know certain sort of tricks. So a better method, however, and much quicker, is to use a dual variational principle. So this is what I have been doing, or one of the things I've been doing here. So the closest paper I've seen related to this is one of Mead and Papanicolaou, who were dealing with the entropy maximization for moment problems, which is very closely related to this. So I'll show you how to do that. So let's write gamma I to be lambda I plus a third. So this is actually the eigenvalues of the true second moment, not normalized. So that the gamma i's are positive, and they add up to 1 now. So the sum of them is 1. And let's write for the vector gamma 1, gamma 2, gamma 3, just gamma. And for a nu in R3, I'll write j of nu to be the gamma dot nu, that's some gamma I nu I, minus the log of the partition function of the parameters mu I. Now, first of all, let's note that if we add a constant to each component of nu, this doesn't change j. So a way of saying that is if you write m to be the vector 1, 1, 1, and you take any real number tor, and you look at j of nu plus tor m, so that's just adding the constant tor to each nu I, then what do you get? Well, you get gamma dot nu plus tor, because the trace of the sum of the gamma j's is 1, and then inside you have minus log of the exponential of sum of nu I pi squared plus tor, because the sum of pi squared is 1, p being a unit vector, and then you take the e to the tor outside, take its logarithm, the tors cancel, and you get gamma dot nu minus log z of nu, which is just j of nu. So that means that if you're considering this, you only have to actually consider it for nu, for example, with nu dot m is 0, because you get all the other values from the values of nu on this hyperplane. So let's consider the problem of maximizing j of mu over mu in R3. So equivalently, just by the remark I just made, that's equivalent to maximizing maximizing j of nu for nu in the hyperplane m perpendicular to m. That's the same thing. So j of mu turns out to be a strictly concave function on m perp, and it goes to minus infinity as the norm of nu tends to infinity on m perp. So and because of that, it attains a unique maximum on m perp. Okay? So how do you check that it's strictly concave and that it goes to minus infinity as the norm of nu tends to infinity? So this is the calculation for the strict concavity. That amounts to showing that the logarithm of the partition function is strictly convex. And so here it is. You just calculate this against some vector a, which is perpendicular to m, and you get this expression, which is, and you see you have a square here, so it's non-negative, and you can check that this, in fact, is not 0 almost everywhere, and so that, in fact, this is strictly positive. I'm not sure whether there's some sort of more general context in which you can see perhaps a simpler sort of thing coming from convex analysis, which would see why this was true, but for me it's just a calculation. Now, to prove that j of nu tends to minus infinity as the norm of nu tends to infinity, so this is where the action is in this particular way of doing things. So of course it suffices to prove that the exponential of minus j nu tends to infinity. And here's the expression for the exponential of minus j nu. And if you rewrite this, or if you rewrite what the argument here is, the exponential, using the fact that the sum of the gamma i's is, this should say, those 2's there are incorrect. That should say 2 gamma 2 minus gamma 1, so raise those 2 powers of 2. But using the fact that the sum of the gamma i's is 1, and the sum of the pi squareds is 1, because p is the unit vector, you get this expression. And then what you do is, you have to imagine now that nu here is going off to infinity. So the sum of the nu i's is 0, so that means that at least one of them has to go off to infinity. So you look at all the cases and you find that there are parts of the, whatever the sort of the signs are for how they go off to infinity. For example, this one could be going to infinity and this one remaining bounded, or this one going to infinity and this one going to minus infinity. You find that there are portions of the unit sphere where these two brackets here have the correct signs to make both of these terms positive, and so their sum goes off to infinity. So that's you have to sort of check the details, but that's the way it's done. So this gives us a proof of existence of the minimizer for the original primal problem, and plus duality principles without any analysis, actually. So you don't. I didn't need to show that AQ was non-empty. That's a useful thing to do for other reasons, which I'll show. The specific function that we construct is useful, but you don't need to do that. The fact that there's a maximizer for J is essentially automatic. We just proved it, and then you get that the maximizer has a zero gradient. At the maximizer, the gradient of J is 0, and then you see that reduces to this expression, that the gradient, in fact, of the logarithm of z of mu is equal to gamma, and that expresses the fact that if you define rho q of p, as in the statement of the theorem, to be this constrained Maxwellian, then in fact there are parameters mu I such that q of rho is equal to q. Okay. And then it's immediate to check that this rho q is the unique minimizer just by convexity. So you take a rho that's not equal to rho sub q, and you use the strict convexity of rho log rho. You have I of rho is equal to the integral of rho log rho. Then you write down the statement that this function lies above its tangent at rho sub q, so it's big equal to rho sub q, logarithm of rho sub q. Then you take its gradient. This is the expression that you get, and you see that the terms when you're integrating rho minus rho sub q against 1 minus logarithm of z mu, that you're just integrating it against a constant, and the integral of rho is the same as the integral of rho sub q, so those go away. And these ones cancel because the rho and rho sub q both satisfy the same constraint. Okay, so therefore you have that I of rho is strictly bigger than I of rho sub q if rho is not equal to rho sub q, and so that rho sub q is the unique global minimizer. So notice that we've got here the dual extremum principle that the minimum of I over A sub q is the maximum of J over R3. So you see that it's really you don't have to worry about this constraint of rho being bigger equal to 0, because in the dual problem everything's done on the whole of R3, right? And all you have to worry about is the behavior at infinity of the function that you're maximizing. Now, the usual Lagrange sort of Fenchel duality principle, which, for example, you can see in this paper, Borwein and Lewis, is actually slightly different. That it says that the minimum of I of rho is the maximum of j hat of mu, where j hat is defined by this. Now, this function in here is the conjugate, is convex function corresponding to the entropy. So somehow the Maxwellians are the conjugate convex function to the entropy. And so, but if you check it, you find that in fact this expression is always less than or equal to the one that we maximize. So actually this is in some sense, if you're asking for bounds, this is a better variational principle. And I'm not sure whether in some sense this variational principle that we use here has some sort of features in some way in the convex optimization literature. I haven't found it so far, but maybe if somebody knows it better than that literature better than me, then that there is something there that would be very interesting to know. So anyway, now let's let f of q be I of rho sub q. So that's this infimum, and so then we get that the bulk energy is this expression T f of q minus kappa q squared. And so you put that into the you put in the formula, and you get this semi-explicit function. So the lambda i's are of course known; they're the eigenvalues of q, and the mu i's. So the only things that are not known here are the mu i's, which you have to get by solving those algebraic equations. And you immediately get that f. So that's the I of rho sub q. So it's the entropic part of this. Is strictly convex in Q, and it does the job. It blows up as the minimum eigenvalue goes to minus a third. So I think it's interesting to see a sort of soft proof of this blow up here. So the strict convexity just follows from the fact that rho log rho is strictly convex. So let's suppose that in fact there was a sequence of Q's, Qj, such that the minimum eigenvalue tended to minus a third, but that f of Qj remained bounded. Then if you hit the Q tensor with Ej and twice with Ej, where Ej is the eigenvalue of Qj corresponding to the minimum eigenvalue, then you'll get that the integral of rho Qj of P times P dot Ej squared tends to 0. But if the f of qj remains bounded, that means that the integral of rho j log rho j remains bounded. And so with a bit of functional analysis, that means that you can extract a weakly convergent subsequence in L1 of S2. And then the limit will integrate to 1. And then you can assume that the eigenvectors tend to some eigenvector, just by compactness of the sphere. And so you pass to the limit, and you get that the integral of rho of p times p dot e squared is 0. But this means that rho of p is 0 unless p dot e is 0. So that means that rho of p is 0 almost everywhere on the sphere, so the integral of rho is 0. So that contradicts the integral of rho being 1. So you see that this is sort of uses the argument I gave at the beginning about what happens when the minimum eigenvalue is equal to minus a third. It's just an approximate version of what I said earlier on. Oh. So you can do better, and you can say exactly how it blows up as lambda min tends to minus a third. So in fact, it blows up logarithmically. So f of q is sandwiched between so c1 minus a half the logarithm of lambda min plus a third, and c2 minus the logarithm of lambda min plus a third. And so these numbers are optimal, I think. And so the proof, now this dual variational principle, it becomes very useful, because once you have a dual variational principle, you can get a lower bound for the for f, and just by choosing a test function, you can get an upper bound. And the test function we choose is the one which we used to show that the a sub q was non-empty. So that's a standard use that's made of dual variational principles in the sort of convex optimization literature. So some other predictions. So all stationary points of the bulk energy with respect to q and are uniaxial, and a phase transition is predicted from an isotropic to a uniaxial nematic phase, just as in the quartic model. And then you could take minimizers rho star of A rho and T without any constraint, and they correspond to minimizing this bulk energy over Q. And these rho star were calculated and shown to be uniaxial by different groups like Fakulin and Slastikov and Liu, Zhang, and Zhang. And actually it was the paper by Fakulin and Slastikov that really motivated this work. And another consequence is that it gets rid of this irritating problem about when L4 is 0. So remember I said that when L4 is non-zero, and if you take, say, the quartic form, or indeed any continuous function of Q for the bulk energy, then the energy is, and any boundary conditions, then the energy is unbounded below. However, when L4, however, if you use this bulk potential, then it's okay for L4 not equals 0 under suitable inequalities on the Li, because you can absorb this nasty term into the other terms. Because since you know that, so this is I4, which was the cubic term that I used. So you see it's of the form sort of QLK, something K, something L. So since Q is bigger than minus a third as a matrix, this is bigger than minus a third times the norm of the gradient of Q squared. You can absorb it into the other terms, provided you make appropriate assumptions about the L1, L2, and L3. Now, near Q equals 0, you can expand this bulk energy, and you get this expansion. Now I've managed to put the KB back in there. It's good. So this was done also by in this paper by Catriel et al. And you see, so in this constant, in this theory, you've essentially got one essential parameter, which is this. Okay? So, and everything else comes out as numbers. Okay? So that gives a ratio of the coefficients, say of the last two terms, which is supposed to be B over C, as 2. Okay? Because the B over C is not quite the ratio of these numbers, but B over C is 2. And if you look in the literature, of course, now the trouble is that these numbers are not often measured, and so I have no idea how reliable the numbers are. But so experimental values we found are for MBBA 1.19 and for 5CB 0.82, which is, well, it's not 2, of course, but on the other hand, the model is pretty crude, and it's not, 10 to the 5 or 10 to the minus 5. So it's within a factor of 2. So maybe that's not too bad. I don't know. But of course, it indicates that you should be trying to do this with better models. Okay. So now finally, I want to talk a little bit about the problem of putting this bulk energy into the full theory. So now I'm going to consider I of Q, which is the integral of CB of Q plus CE of Q gradient of Q, with this singular potential. Okay. So now we know that the integrand blows up as the minimum eigenvalue goes to minus a third. So the question is, under reasonable hypotheses, are the minimum eigenvalues bounded away from minus a third, so that there's some positive epsilon such that the minimum eigenvalue is bigger or equal to minus a third plus epsilon, and therefore less than 2/3 minus epsilon. So this is important because otherwise you can't calculate the Euler-Lagrange equation, right? I mean, again, if you have a Q whose eigenvalue, minimum eigenvalue is not bounded away from minus a third, I try to calculate the Euler-Lagrange equation by taking I of Q plus epsilon P or something. Then that risks having eigenvalues which are less than minus a third, and the integral is infinite then, and you cannot carry out the differentiation. So this is a problem. So you'd really like to prove that this is true. Now, you'd think maybe that was obvious because after all, here's the integrand. You're trying to find a q that minimizes this integral. Now, if this was not true, that would mean that the integrand was unbounded somewhere. Right? It was arbitrarily large somewhere, or in the neighborhood of some point. So that doesn't sound right? I mean, you're trying to minimize an integral, and having the integrand infinite somewhere is not a good thing. However, if you work in the calculus of variations, you know that surprisingly this happens all the time. Maybe I have time just to give a one-dimensional example, which is kind of frightening. So this is something I found a long time ago with my Zell. So the integral is I of u, which is the integral from -1 to 1 of u to the fourth, u to the u to the 6 minus x squared. Is this right? Squared? Something like this. Ux to the 28 plus epsilon ux squared. That's right. The one ux might use the 4. Okay. The x subject to u at -1 is -1, and u of 1 is 1. And this epsilon here is strictly positive. And it has to be pretty small, less than 0.001 or something like this. Okay. So that's a polynomial of a polynomial integrand depending on u, x, and du dx. And because epsilon is strictly positive, its second derivative with respect to du dx is strictly positive. It's bigger than 2 epsilon, and epsilon is strictly positive. So this is what's called a regular problem of the one-dimensional calculus of variations, and it's known that any weak solution of the corresponding Euler-Lagrange equation is smooth. Okay. However, the minimizer of this problem is not smooth, and it actually if you do u against x, this is 1, this is -1, this is 1, this is -1. So the function's got to go through these 2 points here. And actually, the minimizer is something which has a slope plus infinity at the origin. So there's a one-dimensional problem, a polynomial, regular, everything you want. And yet, the minimizer makes the integrand infinite somewhere. So this is not obvious that this holds. So we can do it, provided we take this one constant approximation. So if you minimize this, so elastic terms just k grad q squared, subject to a q on the boundary, say being q0, where the q0 is okay, that its minimum eigenvalue is bigger than -1/3, then in fact the minimum eigenvalue of a minimizer of this is bounded away from 0, and q satisfies the Euler-Lagrange equation. The way we do it, you could do it by sort of maximum principle, but it's slightly more efficient to project onto this convex set where the entropic term is less than or equal to m, for large m. And it can be shown that if you do this for a supposed minimizer, which takes values arbitrarily close to lambda min of q is equal to -1/3, and if you do this projection for large m, then it reduces both terms in the integral, the bulk term and the gradient of q squared term. So it's an open problem, and several people have tried this now to prove this for the case of 3 or more elastic constants. The technique is really wedded to the fact that you have gradient of q squared, and if you do this trick, for example, the gradient of q squared gets reduced by this trick, but a general quadratic function of the gradient of q with more elastic constants does not get reduced. That term does not get reduced by this trick. So the method doesn't work. Now, in the 3 elastic constant case, Craig Evans and Hung Tran have proved partial regularity. So they showed that the minimizer is smooth off a closed set of measure 0, but they don't prove that the minimum eigenvalue is bigger than minus a third. And to end with, just a remark about dynamics. So you could imagine using this bulk energy in dynamics, and the first result in this direction is due to Mark Wilkinson, which you can find on the archive. So he takes a coupled system, essentially with Navier-Stokes equations coupled to something like a gradient flow for the Q tensor, again with one elastic constant, more or less for the same reasons as I just described, and shows that if you start with initial data of finite energy, then these eigenvalues bounds are instantaneously satisfied, even if they're not satisfied actually strictly at the beginning, but instantaneously they become satisfied. So that's some kind of comforting dynamic result. And that's all I've got to say. Thank you.
Okay, the paper is open to questions. On a trivial level, I mean, with the opposite bottom-up approach, RAF, and we have biaxial molecules and biaxial phases, etc. Do you think this rigorous approach could be extended to that case as well?
Well, I mean, the model itself allows biaxial minimizers. I'm not quite sure I understand the question.
Well, in the biaxial phases case.
Oh, I see, yes. You mean, yes, okay, so more complicated order parameters. Okay, I've got the question. Well, okay.
Lagrange minimizers become...
One would need to look at the particular case. I mean, in principle, you might think so, because you might still have a convex entropy, and you just have more complicated constraints, I guess. So it's probably of the same form, because I've not looked at such problems. Right.
Are there any results possible if the elastic constants are nearly equal? Is it? I mean, I guess they are nearly.
That's a good question. I mean, I've talked to Fanghua Lin about this, and he at some point thought he had some argument for this, and that was the sort of hypothesis he was trying to use. But I don't think we have an argument actually yet. So, but it's a good idea to try that. Yes.
There was first.
Oh, yes, for the dynamic problem that is studied by Wilkinson, is that the one that people agree would be desirable for this particular framework, or is?
Well, that's a good question. I am not quite sure about how this Beres-Edwards. I mean, the Beres-Edwards model is essentially, superficially it looks like, say, the Leslie-Erickson equations. You've got Navier-Stokes equations with a term from depending on Q, and in the Q there's an evolution equation for the Q tensor dq dt equals, and then you've got terms coming from the Navier-Stokes equations, of course. But I personally have not sort of looked to see exactly what the relationship is between this and, say, the Leslie-Erickson equation. I don't know, maybe Argia, do you have a comment on that? Or?
I didn't really hear the question,
No.
sorry.
Okay. The relationship between this Beres-Edwards model and things like the Leslie-Erickson equations.
In many models, Beres-Edwards is built such that it reduces to Leslie-Erickson when you put formally Q uniaxial with constant order parameter, and other tensorial models are built so that they're reduced to Leslie-Erickson.
So perhaps the answer to your question is yes.
You said that you can absorb the L4 constant into the other
Yes.
gradient term, but L4 is essential for distinguishing between the actual K1 and K3 Frank constants. So how does that work? And actually, we have measurements showing that L4 is actually even negative, which is perhaps even worse.
Well, the four, okay, I'm not quite sure I can answer your question, but the four Frank constants are given in terms of these four
Yes.
allies by some invertible matrix. So I've not checked in terms of experimental values whether that, whether if you look at the inequalities which allow you to have the existence, if you, of minimizers with alpha not equal 0 would translate into reasonable experimental values for the Frank constant, which I think is the question you're asking.
Yeah, that's precisely the point.
So I mean,
It goes into the old question of existence or not of the K13.
No,
and
this
that,
is
no?
beyond that. This is, the K13 is irrelevant.
Mhm. But still, there are only 4 invariants, so it should be there.
Yeah, so I mean, not really a question, more like a comment. I mean, often people complain that this problem with L4 is like a disease specific to the Q tensor and such, but it seems to me that even in the director model there is a similar disease, which is called K13, so I don't know if this is a general thing.
You thought you eliminated it so quickly.
I was wondering that.
Yes.
Yeah, certainly.
Mich-
Yeah. So, I mean, have you tried to look at the general form of the interaction energy? Because after all, Myers-Alpha model is just the first term of the expansion.
That's a project. I've been embarked on it. But it requires learning a lot of new stuff. I've been trying to do this program.
But apart from this very general one, could you take only one term, but of different rank?
Yes.
So say the Heisenberg, say.
Yes, I mean, so far
Without Q in your
I've certainly thought of doing this sort of thing, but so far we don't have any specific results to report. But yes, this is a very natural sort of thing to do. But of course, I mean, it's going to be more complicated because in the Myers-Sappi theory, the internal engine term depends only on rho through the Q tensor. So when you take a different model, that will not be the case. So you have to handle both terms together. This makes it more difficult, certainly.
Why physically is the minimum eigenvalue of the Q tensor so important? I mean, in my dealings, it's always to do with perfect alignment, which I run into, and the maximum eigenvalue.
Well, that's the same, right? I mean,
Okay.
it's the same condition. I mean, the minimum eigenvalue being bigger than minus a third is implies it's equivalent, I guess, the maximum one being less than.
So you're looking at the problem of almost perfect ordering.
Yes, exactly.
If not, we can thank Professor again.